Hello, welcome you all for this session on derivation of the load vector due to uniformly distributed load. Okay, already we know that we are using the potential equation to derive the stiffness matrix and the load vectors. By the strain energy we can derive the stiffness matrix, and by the work potential we can derive the load vector. Now we are deriving the load vector due to uniformly distributed load. For this we are using work potential. What is the work potential? How much is the load? UDL, it is the intensity is P naught here, P naught, and what is the displacement? That is V. Okay, for we are consider for the small elemental length, that is dx. Okay, this is the work potential we are considering to derive the load vector, where V is the displacement. We already know that for the beams V is equal to H into Q, where H is the Hermite shape functions H1, S2, S3 and H4, where Hermite shape H1 is equal to H1, S2, S3 and H4. It is in natural coordinates. If it is taken in the global or local coordinate system, it can be written as H1 LE by 2 S2, S3 LE by 2 H4. And nodal displacements are at node 1, the displacements are vertical displacement V1, and the rotation or the slope it is dou V by dou zeta. In terms of natural and global coordinate, it is theta 1, that is equal to dou V by dou x. Similarly, at node 2, vertical displacement is V2, and slope or rotation it is dou V by dou zeta at node 2. Or in terms of global or local coordinates, it is dou V by dou x, that is theta 2. So Hermite shape functions, it is in terms of local or global coordinates, and it is in terms of nodal displacement in terms of local coordinates. Okay, substituting the V value here, V is equal to HQ, substituting V value HQ, and dx again it is in local or global coordinates. Okay, it only in the work potential we have substituted V value HQ. If the what is the value of dx? By the relationship between the local coordinate system and the natural coordinate system, we know that x is equal to dx is equal to LE by 2 d zeta. Substituting dx value, it can be written as LE by 2 d zeta. LE by 2 it is taken outside and it is d zeta. Okay, now in this work potential, if the displacement values are removed, then it will be load vector due to uniformly distributed load. Okay, if this displacement values are taken out, then the remaining terms are, it is load vector due to uniformly distributed load. Now you substitute the value of h and differentiate with respect to zeta. We have 4 values of h: h1, h2, h3, h4. Okay, substitute the value of h1, h2, h3, h4 and integrate with respect to -1 to 1 with respect to zeta. Okay, substituting all the values h1, h2, h3, h4 and integrating with respect to -1 plus 1, limits are -1 to 1 with respect to zeta. Then taking the common terms outside, 1 by 4 it is common in all the terms, so taking this is common outside, it is P naught LE by 8. Integration of this term, it is integration of this term, it is 2 into 2. Integration of this term, it is LE by 2, 2 minus 2 by 3. Okay, simplifying it, we have this load vector. Okay, it is for UDL, P naught LE by 2, P naught LE square by 12, P naught LE by 2 minus P naught LE square by 12. Okay, this is the force at node 1, this is moment at node 1, this is force at node 2, moment at, this is the load vector for the uniformly distributed load. Okay, thank you.